Hello everyone. Welcome to the low temperature thermochronology online course, which is a very exciting topic in geology. And this course could be useful to many people in different geological topics. This chapter will be presented by Professor Li Ronqi from Chang'an University. So, we are going to talk about chapter 11, which is the thermal parameters of sedimentary organic matter. The content of this chapter in three main parts, which are: what is the sedimentary organic matter, thermal parameters of organic matter, and applications of thermal parameters to study the basin thermal history. And we will talk about each point in detail, and each part will be presented separately. We hope that you can enjoy this course. After you finish this course, you will be able to know the basic knowledge about the thermal parameters of sedimentary organic matter. Let's start with part 3, applications of thermal parameters to study basin thermal history. The principle of RO here is that according to chemical reaction, there are two basic formulas. First is the kinetics and the second is the Arrhenius. And these formulas indicate that the reaction rate increases with increasing temperature. The change of vitrinate reflectance indicates the change of vitrinate chemistry, and during heating there are a chemical reaction that happens in vitrinite, so the reflectance changes and records the chemical reaction in the vitrinite. These two formulas that you can see indicate that the reaction rate increases with the temperature exponentially and linearly with time. The temperature here is most important than time, and the principle of RO profile is that according to the chemical reaction. So the thermal parameters of organic matter is widely used in reconstruction basin thermal history, and the RO profile is the most used method. The correlation between RO and the burial depth can be expressed in the following regression equation that you can see here. RO equal to A BH. So the RO equal to A multiplied by BH. RO here is the vitrinate reflectance of the sample when it was buried to a depth, a known depth of H, and A is the vitrinite reflectance of the sample without experience burial heating, which is H, the depth here is 0, and the lower value of RO is 0.2. B here is a constant of thermal change of a region, and it reflects the change of vitrinite reflectance RO with burial depth, and it also an important parameter of the reflectance with the subsidence rate of the basin. So the equation 3 can be transformed to the equation 4, and it means that the relation between the logarithm of RO, which is ln RO, and the depth H is a linear equation, and that could be shown the linear segment of the RH diagram. So the line P is the gradient of line segment, and it reflects the heat flow and the rate of subsidence or the uplift of the basin. These two diagrams that you can see show us the RO value is increasing with increasing depth, and the ground fitting here of RO value is 0.2. So the RO here starts from 0.2 and increases with the depth, and also the same for the line RO and the right part of this slide. The RO to H relationship with this, the RO is the finite reflectance and H is the depth. The line segments between adjacent strata shows different fissures. So this is the 4 segment fissures which we will explain in the next slide with the charts. So one line segment with constant gradient length B1 from the top to the bottom is a normal thermal evolution with continuous deposition. So you can see it here in length RO, and it's a continuous deposition with normal thermal evolution that it didn't interrupted by any tectonic events that happen through the time. And here number 2, we can see several line segments with different gradient from line B1, line B2, line B3 with a parallel unconformity between adjacent stratum, and this could be reveals the abnormal thermal evolution under different heat. So you can see it in the second chart here with length B1 to length B2. We have a parallel unconformity between them, and from parallel unconformity, the second one, it has increased the length RO, and this could be a different heat flow that affected by the abnormal thermal evolution under a tectonic history, tectonic events that happened or other affected for the heat flow or the thermal history of the area. Number 3, we can see several line segments with the same gradient from line B1, it's equal to line B2 and equal to line B3, and this with unconformity between the adjacent stratum, which means normal thermal evolution under the same heat flow, which is the third chart here. We can see that length B1, length B2, length B3 is at the same line, that it didn't affected by any abnormal thermal evolution. It's a normal thermal evolution under the same heat flow with the unconformity. Number 4, it's one line segment with constant gradient, while with the part the abnormal value of RO in the middle of the line segment means abnormal thermal evolution with volcanisms. So you can see it here at the last chart. So affected by the volcanisms here, the RO has increased, but this volcanisms event is in short time, so the RO didn't change, because the RO also it needs time to change. So it become again to its normal finite reflectance and become again to the same line F of length RO. So how to get the thickness of denoided or erosional formation? From these two charts you can see in the slides, there are two situations. The first situation from the chart to the left is for the outcrop samples, and the second one is for the sample under the surface with the unconformity. And here we can estimate the thickness of erosion from, firstly, the erosion thickness of one continuous sedimentation. So the finite reflectance RO increases linearly with depth, and that we know. So the regression line through the reflectance data is extrapolated back to RO equal to 0.2 that you can see in chapter to the left here. And we know that after knowing the thermal gradient of the area and the specific degree Celsius that the RO present value reached, the erosion thickness can be calculated. So the thickness between the RO that is reached presently with the RO 0.2, which is the original RO, is the erosion thickness that could be estimated after we said we know the thermal gradient and the heat flow. Then the exhumation rate could be estimated, and to the chart to the right that you can see that we have estimated the thermal maturity, and you can see it by knowing the thermal gradient and the heat flow of the area, and we can correlate it with the present RO and the original RO, which is 0.2, the surface when the organic matter start to deposit. Then we can get the erosion thickness of the strata. So how to get the erosion thickness of discontinuous sedimentation? You see in this chart we have a discontinuous sedimentation with several unconformities, two unconformities here you can see in this chart. So the RO section line here of the stratum below the unconformity surface extends upward, and you can see it extends upward linearly to the top depth point where the RO value is equal to the RO of the bottom with the unconformity, which is dots by the red one. Overlying the formation, you can see, is the bottom surface of the overlying formation. So then this point of the difference in depth is the amount of erosion, and the same method we can use for the second unconformity. So the erosion thickness of discontinuous sedimentation can be estimated from this method. Now, how to estimate and calculate the erosion rate? We know already the erosion thickness, and we calculated from the RO in the previous slides that we now was talking about. So we can calculate the erosion rate by the following formula: ER equal to ZE multiplied by T. So what is ZE? ZE is the erosion thickness estimated from the Fitternet reflectance. This erosion thickness will multiply it by T, which is the duration of the erosion phase in million years. So you can look to this figure, and this strata were deposited in the Cretaceous time, and it suffered from a tectonic uplift, and it started to uplift from the early Oligocene to the late Miocene. So from the early Oligocene to the late Miocene, we have already estimated the erosion thickness by the method of RO used, and we correlated to the original RO, which is 0.2, and we make the difference between the present RO and the original RO thickness. So we got the erosion thickness, which is in this figure is 1550 meter. So now we need to know the duration of the erosion to know the erosion rate. So the duration of the erosion is the difference or the duration by million years between the onset of the uplifting phase till the last of the uplifting phase. So the time between the start of the uplifting phase till the end of the uplifting phase is the duration of the erosion. And here you can see in the figure it's 20.8 million years. So we multiply the erosion thickness, which is 1550 meter, by 20.8 million years, and we can estimate the erosion rate, which is 74.5 meter per million year. So now we know the thickness of erosion, we know the erosion rate, and this method is very effective and very useful in this matter. This is the end of chapter 11. Thank you for your attention.